Chapter 8, Part 5, Carbenes, Oxidation, and Oxidative Cleavage. Carbenes are a really interesting species of carbon. That was a mess. That have a lone pair but do not have a negative charge on them. So carbenes are formed usually by the degradation of an unstable molecule such as diazomethane. So if diazomethane is first deprotonated and then reacted with in heat or light, it will break apart to methylene, which is CH2 with a lone pair, which is the carbene species, and nitrogen. And nitrogen gas, being very stable and also a gas, is going to leave the reaction by the formation of bubbles. It's just going to be gone. And so this reaction cannot reverse back. So once it happens, this species is essentially stuck. Now, if you add in an alkene to a carbene, you're going to end up creating a cyclopropane through a pretty similar mechanism to what we saw previously with halogenation. So you have a cyclic attack of electrons. Carbenoid species, such as the carbene and zinc compound here, do the same thing. Another example of this is dichlorocarbene. And this can be formed by reacting chloroform with an alkoxide, which forms an alcohol and a deprotonated chloroform here, the conjugate base. And then slowly, one of the chlorine atoms will break off to form dichlorocarbene, which is a little more stable than our original structure because there's no longer a negative charge on the carbon. And when reacted with an alkene, this can form a cyclic structure. Notice also that the cyclic structure is on the same face of the ring because, again, it's cyclic, it's a three-membered ring. Those bonds cannot go in opposite directions. So usual conditions for this will involve something like potassium T-butoxide and chloroform. And this is your signal to do a reaction using dichlorocarbene. Okay, let's take a look at oxidation reactions. So one oxidation reaction is the reaction of an alkene with osmium tetroxide and pyridine, followed by sodium hydrogen sulfite and water. This will create a vicinal diol, which is also called a glycol. This is a syn-1,2 dihydroxylation. So again, take note of the word that it's syn. So if you are reacting with a cyclic alkene, this will happen on one face of the molecule. You can also do this using potassium permanganate and hydroxide in water at a cold temperature. And the temperature here is actually very important because if you heat up potassium permanganate with an alkene, a very different reaction will occur. So this reaction can also be done using a catalyst because osmium tetroxide is actually kind of expensive and also highly toxic. It's a heavy metal, and the prevention of creating heavy metal containing waste is pretty important. So let's talk about the reaction first. So the alkene and osmium tetroxide react together to form what is called an osmate ester. This osmate ester is a cyclic structure, which is how this becomes a syn reaction, is because the cyclic structure forms on one face of the ring. And then reaction with sodium hydrogen sulfite and water removes the osmium component there to give you just the diol. Now you can do the same thing with a catalytic amount of osmium tetroxide and reacting with NMO, which is a co-oxidant, the structure of which is over here, at 25 degrees Celsius. So this will do the same reaction, but with a lot less heavy metal waste. Oxidative cleavage of alkenes is another really cool reaction. You can do this under several different conditions. Reacting an alkene with potassium permanganate and hydroxide and water, usually followed by an aqueous acid workup, and also typically done in heat, will break the double bond or cleave it. And we're not just removing the double bond and creating a single bond. We're actually going to separate the two carbons of the alkene. So there's kind of a trend to these reactions. Right now, it looks really complicated, but if you look here, it's actually not at all. If the carbon of the alkene is monosubstituted, such as these pink carbons, note they only have one substitution and the other thing is a hydrogen, then they are going to make carboxylic acids. If the carbon is disubstituted, it will make a ketone. If it has no substitutions on it, it will make carbon dioxide. So that's the trend. That is what I would focus on here. Learn to recognize those conditions, and then remember that each of these make a certain functional group based on their level of substitution. And even more simply, for an unsubstituted carbon, it just makes carbon dioxide. So a common type of problem that you see with this is a predict the starting material type of product, where you're given a formula and given the conditions for oxidative cleavage and the outcome. The goal is to look at the products and figure out what the original product must have looked like. So go ahead and pause and think about this for a second on your own, and then we'll talk about it together. Okay, so the way that I would approach this problem is I would look at each piece individually here. So if this is a ketone, then this carbon obviously was a disubstituted alkene. So the piece of the molecule that we're getting from here is this, and we don't know what's on the other side of it. We can do the same thing for the other piece. This carbon must have been a monosubstituted alkene if it made a carboxylic acid. So the piece of the molecule that we're getting from this looks like this. So now we can combine these two pieces together. I'm going to draw the bigger piece first. On the other side of this alkene must be this piece here. So I'm going to draw those two carbons. So this is the starting material, and I could double check that by counting up my carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, and it would have 16 hydrogens because I see the alkene there. There's another type of cleavage that's really common. This is a reductive cleavage, and it's actually the conditions after the ozone here that make it reductive. So if you react with ozone and methylene chloride at -78 degrees and then follow it up with dimethyl sulfide, you go through a process that's called reductive cleavage. And this follows kind of a very similar trend to what we saw previously. You get a certain outcome based on your degree of substitution. So unsubstituted carbons, such as the one here, will go to make formaldehyde. Let's color code that. So this CH2 group will make formaldehyde. A monosubstituted carbon, I don't have pink, but I have red. A monosubstituted carbon, such as this one here, will turn into an aldehyde. And a disubstituted carbon, such as this one here, will make a ketone. And then there was also a monosubstituted carbon on this one, and it made an aldehyde. So if you can remember that, then you'll always be able to come up with the correct product. So again, focus here. Also notice that previously our unsubstituted carbon in oxidative conditions made carbon dioxide, but in reductive conditions, our unsubstituted carbon makes formaldehyde specifically. So let's do some practice problems. Go ahead and pause and work on this on your own, and then we will come back and work through it together. Okay, so these problems are starting with the same material but going through different conditions. Our first set of conditions is the ozone cleavage with reductive workup. So I know that I'm going to end up breaking apart this alkene. So I'm going to end up with a linear product, 1, 2, 3, 4, 5, 6, 7 carbons long. 1, 2, 3, 4, 5, 6, 7. We can go ahead and number it because that can sometimes help. Now on carbon 2, since this is a di-substituted carbon, I should end up with a ketone. On carbon 7, since it's monosubstituted, I should end up with an aldehyde. So this is the product from our first reaction. And we can do the same thing with our second one, only this time it's oxidative, so we just have to be careful. So 1, 2, 3, 4, 5, 6, 7. Sorry, that got messy. So we have a di-substituted carbon, and the fun thing about the di-substituted carbons is that no matter the conditions, they always make a ketone. And then we have a monosubstituted carbon, and in oxidative conditions, that's going to give us a carboxylic acid. So that is our product from the second reaction.